Hey everyone, I hope you guys have been enjoying CSEdWeek and welcome to the How to Debug. So, to introduce ourselves, my name is Andre Da Silva and I am an electrical and computer engineering major here at CMU, and I have been working at CS Academy for almost a whole year.
My name is Evan Nygaard. I am a music major at CMU, but with a CS minor, and I've been working at CS Academy for over 2 years now.
Hi everyone, my name is Federico van Tienhoven. I'm a business major, and like Andre, I'm also working at CS Academy for a little less than a year.
Yeah, so debugging is hard and confusing, but we know you guys have probably already run into this, and I know I have. But hopefully these techniques that we'll show you will be really helpful when you run into these problems. So let's get started. So first off, an ounce of prevention is better than a pound of cure. So how can we write code with as few bugs as possible? So to get started, we should always write with good comments and good style. So to begin with, making comments makes it really easy to understand what your code is doing and to trace back your code. And writing with good style means your indentations are correct and the names of your functions are names that make sense, and the variables are also variable names that make sense for the variable. In this case, one example here, we have a return true, like the comment tells us what the function is doing. And then the function has a good name, which tells us that it's checking whether it's a palindrome or not. And then the variables, I for index and S for string, tell us appropriately what they should be. Now, another strategy, let's say we do run into some bugs. A strategy to figure out what the problem is print statements. So what we do with print statements is place them strategically in places where we expect there to be possibly an issue. And here we can check variables that affect how our code runs, and we can also check the results and to see whether they are what we expect them to be. And in this example, we have nth prime, where we check the guess and the found, which the found affects how our code is run, and the guess is what we're trying to return.
Another great way to debug is code tracing. Here, this technique, you go line by line and check whether the code is doing what it's supposed to be doing, or you might find a mistake. Therefore, once you get to the end, you'll be able to see if the code actually returned or outputted what you expected, or find a mistake along the way, and it's a great way to fix it.
Once you've done some print statement debugging and code tracing, both of those will help you to isolate the problem and find the area of the code that is really causing the issue. Print statements and code tracing help to understand why the issue is happening the way it is. But then to solve it, unit tests can also be helpful. So with unit tests, you isolate a single component of the code and you change that one component in different ways. It's important to only change that one at a time. And sometimes seeing how the change in that one component affects the entire program can help you actually start to solve the bugs.
A very typical type of error are the syntax errors. These are errors that fail to execute, and you might get a message saying syntax error at line 46 expected, and it might tell you what's wrong with your code. A great way to fix these errors, or to avoid them in the first place, is writing with good style. That's why we recommend don't forget your colons, because this is what students typically get wrong when they start programming. Another type of error are math errors. One reason why we commit math errors are we use hard-coded numbers. This is, for example, just saying that instead of assigning numbers or storing them with well-named variables, we would just use them throughout our code without storing them in well-named variables. That's why this leads to errors, because it's very easy to mistype values and we might need to reuse them throughout our code. So the best solution for hard-coded numbers and math errors in general is storing numbers in well-named variables. Next, another type of math error is using the wrong formula, or similar to hard-coded numbers, just making a mistake with numbers within the formulas. For example, when you use pi times the radius for the circumference instead of 2 times the pi times the radius, can lead to an error. And the best way to fix these mistakes is first, just code tracing, second, double checking the formulas, and third, similar to the hard-coded numbers, assigning the formulas to a well-defined variable. That way you can reuse the formula over and over again. And if you do make a mistake in the first place, you can easily change it once instead of having to change it every time it appears throughout the code. Next, another type of error are logical errors. These are the hardest to find, since the code will run, and it won't give you an error message saying that you've made a mistake, and therefore debugging comes into play. That's why print statements, code tracing are the best way to find errors, specifically logical errors, because you can walk through your code and make sure that whatever you expect the code should be doing, it actually does, since it won't warn you that you made a mistake.
So let's get into the types of logical errors. To begin with, we'll start with missing and extra shapes. So some common causes are logic or math errors when managing shapes within a loop, or referencing the wrong shape. Or yeah, so we have to like watch out for when shapes are on top of each other, for example. And how can we solve this problem? Well, we can use test cases. The unit cases that we have, that we give to you, help you determine whether you have the right shapes in the right places, or if you have too many or you have too little. And you can code trace and check all the loops when you're drawing the shapes and make sure all your math formulas and all random numbers are correctly done. Now we'll move on to index out of range. This is likely caused because you're indexing into a list, which is, and like a point that is either too small or too big. Let's say a list has a length of 5, for example. If you were to index into the 5th index, you have to say the list, name of the list, and then brackets 4. And if you were to put 5, it would be out of range because lists go from index 0 to index 4.
So yeah, in order to solve this error, the first step and the most essential step is to find the line where the error occurred. This should be something where you get a notification in the console, so you should be able to find the line very easily. Once you do that, find which indexing variable caused the error. So like if you index into an array at index I, then you know index I is your troublemaker. At that point, go back a little bit and use some print debugging. Print the variable's value at certain points and ask yourself, how could the variable have possibly been set to that value? And once you find that location where maybe it went overboard or went too small or something like that, then you know where the issue comes from and you can start working on solving it. And the exact solution will depend on the program, but that's how you can kind of determine where this error occurred. So now we're going to do some practice with debugging in actual exercise. So we are going to work on this exercise, which is aircraft control. It's a custom exercise that I made up a little while back. So the idea is that this airplane is taking off, this airplane is coming down, but if we run student code, you can see we have some problems. The airplanes are going completely the wrong direction. So first of all, we want to just double check the code. This is all drawing code, so it doesn't look to be a problem. More drawing code. And now it looks like this is what is causing some of the trouble. So we've got plane 1 dx equals 5, dy is -5, plane 2 dx equals 2, and plane 2 dy is 1.5. And then we have our on step where we kind of play with these dx's and dy's. So the first thing that we can realize is we can just double check all of these. So we can see plane 1.centerx plus equals plane 1.dx and plane 1.centery minus equals plane 1.dy. We can see that this plane 1.dy is already negative. So what if we tried making this a plus equals instead of a minus equals? So if we tried that, it looks like the plane 1 honestly looks the same way as it should with the solution. So it looks like plane 1 is good, but we still got issues with plane 2. So plane 2.dx is equal to 2, and plane 2.dy is equal to 1.5. It looks like if we run this, the plane 2 is moving down still, which is the way it should be with the solution, but it's moving to the left of the solution, but to the right in the canvas. So why does this happen? It happens because in this case, plane 2.dx is equal to 2, and we add this. What we need to do is we either need to subtract this, or we need to make this negative. I would generally err on the side of making the dx and dy variables negative if necessary, rather than trying to subtract them, because this way we can just, this kind of says move it by the change in x, and the change in x can be just generally negative or positive. It works that way in math. So I feel like just making the dx negative or positive versus changing this to plus equals or minus equals is generally more consistent with what we see in mathematical operations. So if we try this now, it all looks good up until there. So once that happens, we're not running along the runway. So why does this happen? It happens because our plane 2.dy just keeps on staying at 1.5 no matter what. This can be a little bit hard to tell because we did not use good comments to explain exactly what our code is doing. We can kind of intuit that this is double checking the place when we actually land plane 2 on the runway. The rotate angle used to be -15. Now the rotate angle is 0. So that should be covering the case when the plane actually lands on the runway. You can see that the rotate angle actually changes when we hit the runway. It just keeps going down. So what we need to do is we need to add something else. We need to reset the change in y to be 0. And once we do that, that'll cause the plane to stop moving down. And that should give us the equal behavior that the solution has. And we can see that that is what it does. So yeah, that is just one quick example of how to debug exercises. So in this case, we saw quite a few math errors. We saw some logical errors where the program ran the way it should, but it didn't exactly do the right thing. So what we had to do is double check our formulas mostly and make sure that they were okay. And using better comments would have helped us to find some of these errors as well, maybe even a little bit more quickly.
Well, thank you guys for watching. I hope you guys enjoyed it and found it very helpful. And I hope you guys enjoy the rest of CSEdWeek. Thank you.
Bye.